We will now try to assemble the element level matrices that we have derived. So, I have written them down for you. We will make a simplification that we have a uniform mesh. So, the element length is constant throughout. Further, we will consider that we have a homogeneous material. What that means is the density, the heat capacity, the conductivity, they are constant throughout the mesh, they do not change with x. We will also assume that the heat source is constant. So, it is a uniform heat source, and that would simplify assembly for us as well. Of course, we do not have to make these assumptions. Finite elements allows us to have a perfectly variable and realistic variation of material properties. But if we make those assumptions, then the mass matrix would have these constants outside, and then it is a 2 by 2 matrix as written over here. That is your stiffness matrix. So, constant heat conductivity, that is your element length, and then the force vector gets fairly simplified. We have these terms Fh by 2, where F is the heat source, and of course, there would be the boundary terms which we are going to not worry so much about. Now, what we want to do is use these element level quantities and assemble them to get the global equations. So, the global equations look in this matrix form, m d dot plus k d equal to f along with this initial condition. So, let me draw a mesh for you, and we will mark certain elements in them, and we will take these contributions from some of the elements and then see how they assemble into the global matrix. So, let us do that. So, first I want to draw a mesh. So, this is the mesh along x. I am only going to draw some elements. So, let us say this is element E, then I have element E plus 1, and I have element E minus 1, let us say. So, I am going to look at 3 elements. I am going to number the nodes also in this manner. So, this is node number E minus 1, this is node number E, this is E plus 1, and this is node number E plus 2. Okay. There are nodes to the left and there are nodes to the right, but I am not going to worry about them. Please also remember that because we are dealing with a very simple problem where the Dirichlet boundary condition is at x equal to 1. So, these node numbers, they also represent the equation numbers. So, it makes my life much easier. So, these numbers can be thought of as either node numbers or equation numbers, and these element numbers I have circled them. So, now let us write down the matrix form, and then we will see how we can assemble these quantities. So, what I first want to do is write down m d dot for u. So, let us say this is the mass matrix M, and it is going to hit this vector which is d dot. So, for simplification, what I am going to do is mark these equation numbers E minus 1 through E plus 2. So, I will mark 4 of them just for simplicity. So, these are of course, there are many more. So, I am going to write these as equation numbers E minus 1, E, E plus 1 and E plus 2. There are going to be certain columns, and these columns are the ones which will identify the unknowns. So, let me identify again 4 of them. So, we are talking about column number E minus 1, E, E plus 1 and E plus 2. So, this is M and this is d dot. In fact, I can erase this from here and write it over here that this is d dot. we can also add to this the K matrix. So, this is going to be the K matrix, and this is going to hit the vector D. And finally, I am going to get the vector F over here. So, I would like to assemble these quantities m d dot plus k d equal to F and use the element level quantities. So, just for the sake of completeness, let me also extend this grid over here. So, roughly speaking, these are again continuation of E minus 1, E plus 1, E plus 2, and I will take the liberty of again identifying 4 columns, which are E minus 1, E plus 1, and E plus 2. And these of course are the quantities in this vector related to equation numbers E minus 1, E plus 1, E plus 2. So, let us first begin with element number E minus 1. So, for element number E minus 1, let me go ahead and put these quantities. So, I start with m first. So, rho CH by 6 is going to be outside. So, let me put that here right away. For element E minus 1, the contributions go to equation numbers E minus 1 and E, these two equations and these two rows. So, in fact, the contributions would go to these 4 entries that I have marked here. So, let me go ahead and enter them. So, I would get a 2, 1, 1, 2. Similarly, when I put them for the assemble the KE, so I would get K by H outside, and I would get here 1, minus 1, minus 1, and 1 over here. And for the vector F, I would get a constant F H by 2 outside, and here I would get a constant 1, 1 in these entries. So, that finishes assembling the element number E minus 1, and now we can start assembling the element E, which I am trying to put in a different color. I hope you can see this on the screen as a yellow color. So, the element level E sends its contributions to equations E and E plus 1. So, these two rows, and of course, the columns corresponding to E plus 1. So, let me mark them. So, for M, the mass matrix, I would get here 2, 1, 1, 2. Of course, they need to be added up. Okay. So, whatever exists there, I need to add, I am sorry, these 1, 2 would come in these. Let us go ahead and make the entries into the K matrix. So, that is going to be to, for the element E, I would have to go to note equation numbers E and E plus 1. So, that is where I would have to go, and these would be 1, minus 1, minus 1, and then I would get a 1 here. And likewise, for the force vector, I would add 1 and 1 here. Finally, I would like to assemble for the quantities for element E plus 1, that is in blue color. So, E plus 1 assembly would involve equation numbers E plus 1 and E plus 2. So, that means these two rows and E plus 1 and E 2, so these columns. So, let me go ahead and assemble them. So, I would write a 2 and a 1 here, and a 1 and 2 here. Similarly, for the K matrix, I would write them over here. So, the quantities are 1, minus 1, and then minus 1, 1, and of course, here I would get 1, 1. Now, I can just add these contents and get my equation numbers. So, what you will notice is that as far as my assembly is concerned, these two equations are actually done, E and E plus 1, because these are the internal equations to the assembly that I have done. They get contribution only from two elements. So, equation E gets contribution from E minus 1 E, I have done both of them. Similarly, E plus 1 gets from E and E plus 1, I have done both for them. But these equations are not complete yet, E minus 1 and E plus 2. So, for simplicity, let me write down equation E. I can write down equation E as rho C H by 6, and then I would have to multiply this quantity, the first quantity, with, because this is column E minus 1, so this would have to multiply d E minus 1, in fact d dot E minus 1. This guy over here is a 4, and this would multiply d dot E. So, I would get 4 d dot E. This one over here would give me plus d dot E plus 1. So, that is what I would get from m d dot, the assembly of this first set of terms. Now, from the stiffness, let us take their contributions as well. So, K times H is on the outside. This is minus 1. So, this would multiply E minus 1. So, I get d E minus 1 plus twice of dE, which is this quantity, and then again d E plus 1 and as far as the F is concerned, I have FH by 2 multiplied by, again I would add them and I would get a 2. So, I simply write this as F times H. So, you can see that the equation that I am getting from this is rho C by 6 times this quantity over here, and then K, I could actually divide this again by another H. So, it would become K by H square, and again remove this H over here. So, if I wanted to simplify this equation further, we are really talking about rho C by 6 d dot E minus 1 plus 4 d dot E plus d dot E plus 1 plus K by H square times dE minus 1 plus twice dE minus dE plus 1, and this is F. Let me call this as A. So, this is what the assumption of a uniform mesh using linear elements and everything being homogeneous gives us. Okay. So, it is a uniform heat source, rho C is same for all throughout, and K is same. Let us take a simple finite difference scheme and see what that gives us. So, I am going to make a simple mesh again, a uniform mesh. This is H. I am going to call this as E, this as E plus 1, and this as E minus 1 to do the same notation. And the equation that we are looking at is something like this, rho c u comma t plus or minus k u comma xx equal to f. So, I am going to write the difference formula for this. As you know, rho and c I would write down at this node E, and u comma t I would write down as u dot at node E, because I am writing the equation at node number E, minus k, and for u comma xx I would write it as u e plus 1 minus twice u e plus u e minus 1 over h square, and this is equal to f. So, let me call this as B. Let us compare A and B. Let us see the first term. In the finite element method, I am getting rho c by 6, and then the d dot term, the time dependent term, seems to have a spatial contribution not just from d dot E, but also from the neighbors. Notice, if I club them all together, if for a moment I convince myself that maybe I should add up all these terms to d dot E, then I would get a 6 times d dot E, and that 6 would cancel out, and indeed I would get the same answer as finite difference. So, that is the first term. The second term, as you can see, is identical, and then so is the last term. So, the only difference that seems to be in these equations is that there is a difference from the FEM and FDM in time dependent term, in the unsteady term. And that was to be expected. If you think about it, the way a finite difference method works is we took the strong form and we simply applied it, we approximated it at each node, and that is what has happened to this term. We simply took u comma t at this node. On the other hand, what we have done in the finite element method is we took this equation and we multiplied it with a w and then integrated over the whole domain. So, what that has done is it has actually taken an integral of this unsteady term over the entire domain, and that is why in the finite element method you get a spread of the unsteady term over the neighboring elements. Okay, so, there is a big difference. So, for the simple steady problem, we saw that if you take a uniform mesh, you take linear elements, the finite difference and finite element method, they give rise to identical equations. Not so for the semi-discrete form of the unsteady problem. You can see this has a spatial component in the finite element method. Of course, we can always approximate this and say that we can lump all the contributions to the central node, and that would be called a lumped mass matrix, which we will talk about. The next step then would be the following. So, now that I have illustrated to you how a typical assembly process looks like and what it does to the element level matrices, we will now set out to solve this problem md dot plus kd equal to f with the initial condition that d0 is d0. There are many methods to solve them, and we are going to look at a very simple method, one of the methods. So, we are going to look at a single step method. To solve the system of ODEs. we will use what is called as a time marching scheme. So, let me illustrate that to you. What we will assume is that if this is the time axis, then we will say that there are many discrete levels at which we want the solution. These are different time instants. So, just like we have made a mesh along the x, we can also make some kind of a mesh along the time direction. Let us say this is time level n, this is time level n plus 1, maybe this is n minus 1, this is n minus 2, and the time level 0 is somewhere far below. In a time marching method, we assume that everything is known at level n and below. So, these are known, and we will seek to find solution at time level n plus 1. So, we will make a finite element mesh and we will start estimating the solution on it using these equations. So, we will reach, let us say, the time level n, and everything is known here, and the challenge now is how to get the values at n plus 1. So, we will look at them.